Good day. We get to start the very last concept in this chapter, which actually puts together all the other things we've been doing along the way. Very exciting moment. We're going to be graphing polynomial functions. In order to do that, we're going to use a lot of the things we've talked about along the way. Here we have, for instance, a polynomial function that we're eventually going to graph. They're asking us, first of all, since plotting zeros is the most important thing to do, once you've found all the zeros of the function, you have done, like time-wise, probably 80 to 90% of the work in making the actual graph. So we're going to start with that. We're going to figure out how many positive roots are there. And, well, there won't be any because all the terms are positive. There are no sign changes. So we already know that none of our roots are going to come to the right of the origin. So let's talk negative roots. If we plug negative x into the function, we get some of the terms change signs, but if we count how many of them, or how many changes there are, we go positive to negative, that's a sign change. Negative to a positive is a sign change, that's 2. Oh my goodness, there's a bunch. This one's 3. And then negative to positive again is 4. 4 sign changes means you could have 4 or maybe 2 or maybe 0 negative roots. Then they want you to figure out how many imaginary roots there are. Well, I'm going to make a table down here to help figure that out. I know no matter what, there has to be 4 total roots because that's the degree, that 4 is the degree of the function. There has to be 4 roots. We've already figured out that there are no positive roots, so I'm just going to fill in 0 on all those rows in the positive column. And we know that you could either have 4 or 2 or 0 negative roots. That is why I made this table 3 rows high below the heading. So the imaginary roots, let's see. If we have no positives and 4 negatives, that means there won't be any imaginaries because we've already reached our total of 4. If there's no positives and 2 negatives, that means we'd need 2 imaginaries to give us a total in that row of 4. And if there aren't any positives and there aren't any negatives, that means all 4 of the roots would have to be imaginary. All right, let's talk end behavior. If you look at the dominant term in this function, we see that it's 2x to the 4th, and that tells us all we need to know about the end behavior. First of all, since there's a positive coefficient and the power, or the degree, is even, that means we're going to have end behavior kind of like you would see on something like y equals x squared, which has the same traits. Positive coefficient, even power. If you know anything about the graph of y equals x squared, you know that both ends are opening up, so it'll be high on the left and high on the right. Then we need to figure out where the zeros truly are. We're going to use the rational roots theorem to help us. That box isn't hiding anything. That was tricky. The rational roots theorem is going to help us figure out exactly where the roots are for this graph. We've got to make a list, first using all the factors of the constant term at the end of the function. It's weird to start at the end, but that's how rational roots theorem works. We're going to look for anything that'll go into 6, like 1, 2, 3, and 6. They all divide into 6. We use plus and minus for each. And then the denominator is going to be formed by all the factors of the lead coefficient. In this case, all of the factors of 2, which is just 1 and 2. We don't need plus and minus in the bottom because we've already got it in the top. Then we make a whole bunch of fractions. We make a fraction where every of those possible numerators is placed over all those possible denominators. If we do that, we get 1 over 1 would be 1, 2 over 1, 3 over 1, 6 over 1. That just gives you those 4 numbers there. Of course, you need to put those same 4 numerators, each of them over 2, and you get a half, 2 halves, 3 halves, 6 halves. Of course, 2 over 2 is the same thing as 1, and we already have that in our list, so bye-bye. Same thing with 6 over 2. That's just 3, so take that 6 over 2 and bye-bye. Our next step becomes figuring out which of these candidates are actually going to give us roots in the function. That's what they want us to do here. Plot the actual roots of f, and then you can draw the graph soon after. Here's a little scratch paper. So the numbers we were going to try were plus minus 1, plus minus 2, 3, 6, and then a half, and 3 halves if need be. But we already know that none of the roots are positive. Haha, Descartes' rule, right? There are no sign changes in the function, which means don't waste your time plugging in positive numbers, because they won't work. They won't give you a 0 for a remainder, which is what we want. So if you set up a synthetic substitution problem and run -1 through it, you do not get a 0 at the end. However, there's still value in that 5. Because if we were going to graph that graph, we'd know that if we plug -1 in, we would get 5 for our y value. So I would, at this point, go to the actual graph and plot -1, 5. I can't do that right now, but you could do it in your notes. I can do this, though. Haha. I'll just make a note for later. The other thing I'd do really quickly is I would find the y-intercept. You get the y-intercept by plugging 0 in for x, and when you plug 0 in for x, you get real easy math. 0 plus 0 plus 0 plus 0 plus 6. So when x is 0, y is 6. It's kind of like the free space on a bingo card. I mean, they're giving it to you. It's pretty minimal effort to cover it up. Why not just go ahead and do it? Okay, back to the drawing board, literally. Let's try a different number. Let's try -2. I'm going to run that through synthetic substitution. Hey, we get a 0 this time. So now we also have a depressed polynomial with it. It still isn't a quadratic. It's still got that third power on it, but we're way better off than we were with a fourth. And we got -2, 0 as one of our roots. I'm going to make a note of that over here. You can go ahead and plot it right away. Now you got options here. You can either continue guessing and checking. If you continue guessing and checking, use these depressed polynomial coefficients in your synthetic substitution. Because that way, if you find one that works, you'll then be down to a second power function, and hopefully you can just unfoil it from there. If you go back to the previous equation, even if you find one, you'll still get another third power function back, and you'll have to keep guessing. So I would definitely take advantage of that depressed polynomial. So you can do one of two things. All right, you can keep guessing and checking, or if you remember how to factor by grouping from any previous math classes, that'll get you there a little quicker than guessing. My GCF, if I try to factor all 4 terms, I get 1 for my GCF. But if I just look at my first couple of terms, I can at least take a 2x squared out of those. I'm going to take that 2x squared out of just the first 2 terms. So then I would have to put back an x to get the first term, plus a 3 to get my second term. Put that aside for now. Now I'm going to focus on the last two terms. I'm going to put a plus in here because there is a plus in the problem. But I can look at my GCF of those last two terms, and you might go, well, the GCF's 1. How's that help us? Well, fine. I'm going to literally park a 1 out front, and then in a set of parentheses, put in the x plus 3. And you'll notice there's an x plus 3 that's common. So if I look at this as a whole new problem from scratch, I'm going to say, well, there's an x plus 3 in the first term and an x plus 3 in the second term. That's common. I'm going to factor out that x plus 3. And then in a set of parentheses, I'm going to put a 2x squared back for the first term plus a 1 for the second term, because those are the things that are left over. If you were to distribute that x plus 3 through, you would end up with that previous step that you started off with. If you're going to keep guessing and checking, you can see that -3 would probably be a good next guess. But if you've done the work by factoring by grouping, then you already have that apparent. Here's what we got. -1,5, we had that from before. 0,6 we got from plugging in 0 for x. -2,0 we got from guessing and checking. -3,0 we got from factoring by grouping. And now I got to set that other factor, 2x squared plus 1, equal to 0. That's not going to factor. It's not a difference of squares. It's not a difference of anything. It's a sum. But you can subtract the 1 and then divide by 2 and then put a square root in, which of course will give you a plus minus when you put a square root into a problem. And you'll have plus minus square root of -1/2, better known as plus minus square root of 1/2 I, which means you got not one but two imaginary roots that are not going to show up when you graph the function. But that's fine, because it means we've got 1, 2, 3, 4 roots all accounted for, and that means you can stop looking for roots because there aren't any more. So now we can jump over to the graph, plot the points, and make an actual graph. So there's our point, -1,5. We got 0,6 from our Y-intercept. We got the two real roots that we found were -2,0 and -3,0. The other two roots were imaginary. By plotting these roots and plotting these 2 points up here, we've done the bulk of the work of getting this thing graphed. And I just now realized that I did my arithmetic wrong about 10 steps ago, and that's not -1,5, that's -1,6. Ugh. Someone get a math teacher in the room. It's very important to plug in x values in between any pairs of roots that you have. So I'm going to find out what happens when x is -2.5. If we plug -2.5 into the function, I'm just going to grab a calculator, figure out what that'll be. Now remember, when you're plugging a negative number into a polynomial function, it is very important to put the negative number in parentheses before you send it to a power, or else your calculator will interpret that differently than you mean it. The order of operations will give you a result that you aren't supposed to be getting. So you should get -3.375. If I plot that on the graph, now, how precise do you have to be when you're graphing this? Well, I don't know. Do you think I'm going to be able to tell the difference between -3.375 and -3.4? No. I mean, get somewhere close. So now we know our graph is coming down through here, probably bottoming out somewhere around here, coming back up, and then it must be kind of wiggling through these 2 points, because it's got to go high off that rightmost point, and and then down and then back up again. That's good to know. Let's plug in one more thing. Let's plug in like negative 0.5 to see what's going on between these two high points. I'm getting 5 and 5/8. I'm going to plot that there. Okay. So now since we know the graph's going forever up from the leftmost root, it's also going up from the rightmost root. Now we can kind of fill in the rest of the graph. My final graph should look something like that. They obviously have more detail on their graph than you have on yours, but that's fine. If you have the roots in the right spots and you got the end behavior going in the right way, and you've maybe filled in a couple high and low points along the way by plugging in numbers between the roots, then you've really done pretty well for yourself. That's what I'm looking for. With the second example, you first want to be in the habit of saying, hey, what's the GCF? Because really, ultimately, we're just doing big factoring problems, and the first thing you should ask yourself anytime you factor is a GCF. Here, if you're really on your game, you'll notice that there's an x that you can factor out of every term. So f of x is going to look more like this. All the powers in the parentheses here are going to drop by a power. It also means that if you set each of these factors equal to 0, like this one, it'll have 5 solutions, but I don't know what they are yet. But I do know this one. If I set this factor equal to 0, x will be 0. Therefore, 0 is going to be a root for this function. We could go right to the graph right now and plot a point at 0, 0. But there are still 5 other roots to be found, so let's start going through Descartes' rule. There are 2 sign changes. We go from negative to positive, and then later we go from positive to negative. 2 sign changes means there could be 2 or 0 positive roots. For the negative roots, if you plug negative x in to the function, you get this result. There is 1 sign change right away, negative to positive, in this function. We find there's only 1 negative root, which means when we graph this, we should only see the graph crossing the x-axis 1 time to the left of the origin. Now, I had to put another column in this table because since 0 is a root, I should also say, well, one of the roots has to be 0, which doesn't fit into the other categories. It needs a category of its own. And I know that there are 6 total roots, so I'm just going to fill that in right now. I know that there is 1 negative root, so I'm going to fill that in right now. And I know that there are either 2 or 0 positive roots, which is why I have 2 rows in this column, or in this chart. With that in mind, if I add up 1, 2, 3, 4 roots, that means I need 2 more to make a total of 6. In the low row, I get 1, 2 roots accounted for. That means I would need 4 more to get a total of 6. So there will either be 2 or 4 imaginary roots that are going to be not showing up on this graph. The end behavior, well, we have a negative x to the 6th as a dominant term, that has a negative coefficient, an even degree, kind of like the equation y equals negative x squared, which is an upside down parabola, which means we'll be down on the left and down on the right. Let's find the roots. Rational roots theorem. We need to list the factors of the last term. I am using this depressed polynomial and not the original because the roots for the depressed polynomial will also be roots for the original. So I'm going to list all the factors of 8, and I'm going to list all the factors of mercifully 1 for my denominator. I know it's a negative 1, but it doesn't matter because you already got your plus and minus in the numerator anyway. If I make a list of those, 1 over 1, 2 over 1, 4 over 1, 8 over 1, you just have 1, 2, 4, and 8. Now is the part where we need to figure out which of those candidates actually give us a 0 for real. The roots could be positive or negative. Descartes' rule didn't rule out that there could be positive roots, but it's a possibility that there might not be any. I'm going to start with the negatives then, because it says for sure there's a negative root. Now, the negative 1 didn't work, and I can't even plot -1, -9, because I'm not using the original function. I'm using a depressed polynomial, so the y values will be different. The zeros would be the same, but the other y values will be different. So I'm going to have to try something else. Try -2 here. If this doesn't work, I'll zip ahead a bit. It is not looking good. Yeah. I don't know what we're going to end up with, but it's not going to be these. Okay. I tried a bunch of stuff. I tried all the negative possibilities. None of them worked, which doesn't mean there isn't a negative root. It just means it's not a rational root. It's probably like a negative square root of something. So I started trying positive roots. I tried 1, it didn't work. I'm feeling okay about 2 though. Let's see here. I don't know why I would give a problem that's so mean that even 2 wouldn't work here after trying all these other possibilities. Ah, thank goodness. All right. So we know that 2 is a root. We also know that 0 is a root because we factored out an x. So on my graph, I would go ahead and plot 0, 0. I would plot 2, 0. Now with this, we're also getting a depressed polynomial. This is -x to the 4th now, plus 4, the constant term. There's no x cubed, there's no x squared, there's no x. So this is our depressed polynomial. We could just, we could add this over, get 4 equals x to the 4th. I guess you could take the square root of both sides. Of course, when you do that, you need to put a plus minus in with your square root. So plus minus 2, and the square root of x to the 4th is x squared. Then I could take the square root again, which will give me another plus minus sign. And in the end, I'm going to end up with 4 answers. There's the square root of positive 2. There's the negative square root of 2. There is the square root of negative 2. And there is the negative square root of -2. This is about 1.4 if you punch it into a calculator. So then this is about -1.4. These are real numbers. These, though, are square roots of negatives, and they are imaginary numbers that are not going to show up on the graph. So here's what we've got to plot for our roots. We can plot x equals 0. We factored out an x. We can plot x equals 2. We found that through trial and error. We can plot x is about -1.4, and x is about +1.4. So we have our 4 roots plotted for this function. We know the end behavior is going to be going low on the left and low on the right. So you find the 2 roots that are furthest apart, and you can draw your end behavior right off of there. Which means our graph must be coming up through here, reaching a maximum somewhere, I don't know where, before it comes back. What I'm going to do is I'm going to plug -1 into the function, and I'm going to see what y value it starts to reach that maximum at. Function, I believe you get 9. And if you, let's see, so the graph comes up, it hits somewhere around 9, maybe gets even a little higher, comes back around, hits the origin, trenches out somewhere in here, I don't know. To figure out how low it goes, I could figure out something like +1, because that's an x value in between these roots. So if I plug in +1, I get, let's see, -3. I'm going to plot that. Then the graph is going to come up yet again. It's going to top out max somewhere in this ballpark, I guess. It's going to buckle back around though, because the end behavior is supposed to finish low. So here, you'd have to plug in something kind of obnoxious, like 1.7 or something like that. And if you do that, you get like 2.2. I'm going to plot the point 1.7, comma 2.2. And then you can draw in your graph from here. It should end up, if you start with the end behavior and then sort of slalom your way up and down the slopes, you get something that should look sort of like that. All right, so to summarize all this, steps to graph a polynomial function, which you'll have to do about 4 times on the next assignment. You'll have to, first of all, find the roots. You can use Descartes' rule to narrow down your options sometimes. You might as well plot the intercept. That's like the free space on a bingo card. And you can draw the end behavior based off, or coming off of the 2 furthest endpoints from each other, the 2 endpoints out at the extremes. Finally, plug in some x values in between each pair of roots. And that'll give you the sort of how high is it going, how low is it going when it's roller coastering through the middle of the graph. Once you have all the points, you can draw a smooth curve through it. It's not like a rigid dot to dot. Just give it a little swagger, give it a little contour to it. But once you've found the roots, the first step, you've really done about 80% of the work. So go ahead, give it some practice on the homework, and let me know if you run into